Welcome to The Explainer. Today, we're taking some pretty heavy academic software design principles and transforming them into clear, actionable knowledge. I absolutely love taking an intimidating wall of theory and just breaking it down into something you can immediately see and use. So, have you ever stopped to wonder, how do engineers manage massive, complex software systems without them just, well, breaking? I mean, think about it. The apps and systems we use every single day literally have millions of lines of code. How on earth do professionals keep it all from falling apart the second one tiny thing changes? Well, that is exactly what we're going to figure out today. Here is our roadmap for today's explainer. We're going to cover taming complexity, low coupling and high cohesion, interfaces, object-oriented design basics, and then we'll wrap it all up with a real-world recycling machine case study.
All right, Section 1, Taming Software Complexity.
Let's identify the core villain of our story here. It's complexity itself. Software is inherently complex, right? You absolutely cannot build a massive program as just one giant continuous block of code. It'd be a nightmare. Because it's so incredibly complex, engineers have to break it down into smaller, much more manageable components. And to do this successfully, without creating a giant mess, they rely on two top-level design paradigms. Which brings us to Section 2, low coupling and high cohesion. These two paradigms, they are basically the twin pillars of software architecture. So think of low coupling as looking outward at the relationship between different modules. You really want minimal dependency there. Different modules should have very limited knowledge of each other. Now, high cohesion, on the other hand, that looks inward. It's all about the relationship within a single module. The elements inside a specific component should have a really strong, highly focused relationship. They should all be working together toward a single, well-defined purpose. And when you combine these twin pillars, the shared benefits are just incredible. First, you get enhanced reusability. Why? Because a highly cohesive module with very few outside links can easily be picked up and just dropped into a completely different project. You also get improved maintainability and testability. This is huge because it means you can test and fix one single component in total isolation without accidentally causing some catastrophic chain reaction everywhere else in the code. Ultimately, what you get is a truly flexible, modular design. Moving right along to Section 3, interfaces, the gatekeepers. So to actually guarantee this low coupling we just talked about, we use interfaces. Think of things like APIs or user interfaces, which basically act as strict gateways between components. Let's use an analogy. Imagine you're designing a self-driving car. You really don't want the code for the gas pedal talking directly to the code for the engine's pistons. Because if you did that, a simple update to the pedal might literally break the engine. No way. Instead, you use interface controllers sitting right in the middle. The gas pedal asks the driving controller to speed up. Then the driving controller talks to the engine controller. Finally, the engine controller tells the piston to go faster. See how that works? The outer world absolutely doesn't need to know the messy inner workings of the engine. It just talks to the interface.
Okay, Section 4, Object-Oriented Design Basics.
To actually build these interfaces, programmers rely on object-oriented concepts. And let's kick off this quick glossary with classes and objects. A class is simply a blueprint, plain and simple, while the objects are the actual concrete instances built from that blueprint. So even though every object built from a specific class might have different attribute values, like different states or data, the actual behaviors they are allowed to perform are exactly the same. And we trigger those behaviors by sending a message to the object. For example, calling a method that just says jump. Now, to keep all these objects from breaking each other, we use something called encapsulation. The absolute crucial point here is keeping internal states strictly private. You want to hide everything the object needs to do its job from the outside world and only expose very specific public behaviors. Going back to our car analogy for a second, the engine encapsulates the messy, complex explosions of gasoline, right? It hides all that and just gives you a simple interface to make the car move. Next up is inheritance. When objects share traits, we use inheritance to create an is-a relationship. Think about it like this. A manager inherits all the base traits of an employee, but then adds some specialized permissions on top. The manager class automatically gets all the basic characteristics of the employee class, but, it can also have its own unique, specialized traits. And driving all of this is polymorphism. That literally means having many forms. It allows different objects to respond to the exact same message in completely different ways, specific to their type. Here's a fun way to picture it. If you send the jump message to a young child object, you're going to get a very different, energetic response than if you send that exact same jump message to an old man object. The message itself is exactly the same, but the resulting behavior totally changes based on the specific object receiving it.
All right, let's bring it all together in Section 5, Case Study, Recycling Machine.
Let's take all this abstract theory we've been talking about and actually put it into practice. We're going to look at Ivor Jacobson's classic recycling machine case study. Grounding this in reality, imagine a physical, real-world automated recycling machine. The use case here is pretty straightforward. Customers walk up and return bottles, jars, cans, or even crates. The system has to register exactly how many items are returned, check their type, and then, when the customer is all done, print out a receipt with a total return sum so they can get paid. Now, to program this machine using the principles we just learned, we really have to realize that object-oriented design is ultimately all about responsibilities. Inside this machine, we're basically treating the software objects exactly like employees in a company. And just like employees, they have very distinct job descriptions. These responsibilities are split into two main categories: knowing and doing. Let's compare these two because it's super important. If an object is responsible for knowing, its whole job involves holding on to private encapsulated data, knowing about other related objects, or calculating derived values. That's it. But if an object is responsible for doing, well, its job is taking action, initiating actions in other objects, or just controlling and coordinating activities across the entire system. So let's look at how specific components in our recycling machine handle knowing. A single deposit item, like, say, a soda can, knows its own private data, like its number and its monetary value. The customer panel knows about the deposit item receiver, so it can easily send messages to it. And then there's the receipt basis. Kind of think of this one as the system's accountant. It knows about all the items that have been inserted, so it can mathematically compute that final total sum. Notice how highly cohesive they are. They know their specific data and absolutely nothing else. On the flip side, we have the doing. The receipt printer does the physical action of actually printing the receipt. The customer panel initiates the classification process the second a customer interacts with it. And perhaps most importantly, the deposit item receiver acts as the big boss, the manager. It controls the overall system behavior by delegating and assigning tasks to other objects. Like it's the one telling the receipt basis to calculate or telling the printer to go ahead and print. It just coordinates all the activities seamlessly. So by keeping that coupling low and cohesion high, and by really carefully assigning those knowing and doing responsibilities, engineers are able to make these incredibly complex machines run flawlessly, day in and day out. Next time you use an automated machine at the grocery store, I want you to ask yourself, how are its hidden objects talking to each other right now? Which component is the manager in there, and which one is the accountant? I promise you, it completely changes how you see the technology running our everyday world. Thanks so much for learning with me today on this explainer.